It's an immense pleasure for me to welcome you all to this special lecture inserted in the webinar series of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. Today, we will have the honor to listen to Professor Steven Weinberg, who was awarded with the Nobel Prize in Physics in 1979, together with Sheldon Lee Glashow and Abdul Salam, for contributions to the theory of the unified weak and electromagnetic interaction between elementary particles. Our special guest is a professor of physics and astronomy at the Universities of Texas, Austin, in the United States of America. Apart from the Nobel Prize in Physics, Professor Weinberg's research on elementary particle physics and cosmology has been honored with the U.S. National Medal of Science, the Benjamin Franklin Medal of the American Philosophical Society, the Denny Heinemann Prize for Mathematical Physics, and numerous other awards. He has been elected to the National Academy of Science of the United States, Britain's Royal Society, and other academies, and holds more than 15 honorary doctoral degrees. Professor Weinberg is the author of numerous books, including The First 3 Minutes, which inspired a myriad of young, curious people of all ages worldwide, including me, and I'm sure that many others who will be listening to him today. I can also mention the classical textbook, Gravitation and Cosmology, which guided generations of physicists in these research fields. More recently, Professor Weinberg wrote the textbook Cosmology and the series The Quantum Theory of Fields, the latter constituting in a collection of 3 excellent volumes which should be present in every physics department library. It is precisely about the future of quantum field theory that Professor Weinberg will tell us today, and I should not make you wait longer to listen to him. Professor Weinberg, thank you very much once again for having accepted our invitation. The audience is yours.
Thank you very much, Professor Crispino. It's a great pleasure and an honor to be able to talk to you this afternoon without actually having to get on an airplane. I am going to be talking about the quantum theory of fields, which is at present the basis for our deepest understanding of matter and force. I will try first to put it in some historical perspective and bring the story up to the present, and then look into the future and try to anticipate what in future physics will be the role of the quantum theory of fields. The quantum theory of fields, in a way, is as old as quantum mechanics itself. In 1905, Einstein applied the idea of the quantum to radiation, to the electromagnetic field, making the hypothesis that the energy of electromagnetic fields is packaged in little bundles that were later called photons, carrying energy and momentum, and use this idea both as a basis for understanding the nature of black body radiation, the radiation emitted by heated bodies, and also new predictions regarding the photoelectric effect, which were then verified. Quantum mechanics reached its mature form in the 1920s through the work of Schrödinger and Heisenberg and Born and others. Work that was mostly in the application of quantum ideas to particles, in particular to the electrons in atoms. And so by the end of the 1920s, physicists had a rather divided view of nature, far from unified. On one hand, there were particles of the electron, the proton, whatever else was in the nucleus of the atom. And on the other hand, fields, the electromagnetic field, treated differently, very far from being treated in a unified formalism. The effort toward unity began in the late 1920s and the early 1930s with work of, particularly of Heisenberg and Pauli, and then Pauli and Weisskopf, who invented other sorts of fields besides the electromagnetic field, and showed how quantum mechanics could be applied to these other kinds of fields. Fields that were not known in nature, but that served as a test for their ideas. The first application of quantum field theory to the real world outside the scope of electromagnetism came in the early 1930s with the theory of nuclear beta decay by Enrico Fermi, in which fields were introduced for the proton and neutron and electron and neutrino. And Fermi wrote down an interaction that would account for the transmutation of a neutron into a proton with the emission of an electron and a neutrino. Fermi's theory was very successful in predicting the distribution of energy of electrons in beta decay. And that prediction really hasn't changed to the present time, although Fermi's theory needed to be modified in order to account for the way beta decay obeys various selection rules, and then to take account of the violation of left-right symmetry. Fermi's theory is, with these modifications, still our current best theory of beta decay in the lowest order of approximation. Theorists began to push quantum field theory, especially quantum electrodynamics, in the 1930s beyond the lowest order of approximation, taking into account processes, for example, in which an electron, while it's in the Coulomb field of the nucleus of the atom, would emit and then reabsorb photons, which never became real. We call them virtual photons, but still would affect the energy and other properties of the electron in its orbit. And a trouble was discovered. In particular, Robert Oppenheimer and Ivar Waller, a Swedish theorist, independently discovered that in these calculations, which go beyond the lowest order of approximation, dealing with the emission and the reabsorption of photons, results turned out to be infinite. That is, if you ask what the energy difference is between two states in the hydrogen atom, say the 2s and 2p states, which in the lowest order are degenerate, have the same energy, the answer in the next order of approximation would be that it's infinite. This is not a satisfactory result. Philosophers and theologians may talk about infinity, but when physicists are trying to predict something that can be compared with experiment, infinity is not a satisfactory answer in a theoretical calculation. This problem of infinities was the bone in the throat, to use a Yiddish metaphor, for theoretical physicists throughout more than the next decade. there was an idea floating around due to Kramers and Weisskopf and probably others that perhaps these infinities just went into redefining what we mean by the constants of the theory, the charge and the mass of the electron. But nobody could make that work. The reason was that in this period, until the late 1940s, the only calculational technique that was available was one called old-fashioned perturbation theory. Quantum electrodynamics is a theory consistent with special relativity, of course, and in fact, indeed, special relativity was invented as a symmetry group that would leave the equations of electrodynamics invariant. But the calculational method, this old-fashioned perturbation theory, did an excellent job of hiding the relativistic invariance of the theory. And with it, no one could see what was happening. It was just hopeless. In the late 1940s, after the war, several theorists independently discovered how to do calculations in quantum electrodynamics in which relativity, consistency with relativity was maintained at every step. These were Richard Feynman, Julian Schwinger, and Shinichiro Tominaga with a number of collaborators. They independently developed techniques for the calculation of physical quantities in quantum electrodynamics. They found that indeed the infinities could be absorbed into a redefinition of the constants of the theory. For example, there's a constant m in the equations of electrodynamics that stands for the mass of the electron. But it stands for the bare mass, that is the mass the electron would have if it were not surrounded by a cloud of photons that it was continually emitting and reabsorbing, which in fact it is. When you calculate the effect of that cloud of photons, you find it's infinite. But that mass, the m in the equations, might itself have an infinity which cancels the infinity in your calculations of the effect of this cloud, leaving a finite remainder, the mass of the electron, a finite number that we can take from experiment. The same was done with the charge of the electron and other infinities. It was found that all infinities in the theory could be eliminated in this way. Wonderful. They could do calculations. Calculations were done to many decimal places, such as a calculation famously by Schwinger of the strength of the electron's magnetic field. And they were found to agree with experiment to many decimal places. In fact, it was today, quantum electrodynamics in its agreement with experiment is, in a purely numerical sense, the most successful theory ever in science. Wonderful. This is what was on everyone's mind when I was a graduate student in the 1950s. I had to learn this. It was tremendously exciting. It was less than a decade old. I found actually Tominaga, Schwinger, and Feynman difficult to read, but Dyson, Freeman Dyson, had put it all together in a beautiful way. It's still a good way to learn the subject. He had shown that this cancellation of infinities works to all orders in perturbation theory. And Dyson also explained why the Feynman diagrams, which for Feynman were an intuitive way, independent of mathematical formalism, of calculating things in electrodynamics, Dyson showed why that actually works, why that reproduces what you get when you apply quantum mechanics to the theory of electrons and electromagnetism. There was something about this marvelous advance that I think impressed me probably more than it impressed most people. Most people were, I think, very happy that now calculations could be done and the bad old infinities had been tamed. But for me, this process, by the way, the cancellation of infinities by a redefinition of the constants of the theory is called renormalization. What struck me as really exciting, beyond anything else, was that renormalization provided a technique for discovering the correct theory. It wasn't just a way of doing calculations, it was an engine for eliminating the infinite number of possible theories that theorists can think of and focusing on the correct theory. The point is that in most theories that you can write down, that theorists can imagine, this process of canceling infinities with redefinition of a finite small number of parameters like the charge and mass of the electron doesn't work. It is only some theories in which this works. And if you want to avoid infinities, as we must, these, I thought, were necessarily the theories that would describe nature. It's wonderful to have a way of learning theoretically what kind of theory can describe nature. To take a very practical example, as I mentioned, one of the great successes of quantum electrodynamics was Julian Schwinger's calculation of the magnetic strength, the strength of the electron's magnetic field, what they call the magnetic dipole moment of the electron. Well, in fact, if you write down the most general theory of electrons and photons consistent with fundamental principles of quantum mechanics and relativity, you find the magnetic moment of the electron could be anything at all, could be anything you like. There are terms you can add to the original version of quantum electrodynamics that would make the magnetic strength of the electron anything. Those terms, however, would destroy the renormalizability of the theory. That is, they would destroy the wonderful feature of the theory that infinities cancel when you redefine a small number of parameters. And so we really know, I thought, why the theory is what it is. It has to be that way, otherwise you would have impossible infinities. I and many other theorists thought, well, perhaps we can go beyond electrodynamics and develop a renormalizable theory of everything, of not just electromagnetic interactions, but the other interactions that were known to act on elementary particles, the weak and strong interactions. It would be a theory involving obviously more fields, not just electrons and photons, but fields for other kinds of particles. It would involve symmetry principles beyond the symmetry principles that govern electrodynamics. Of course, we knew it would have to be a more complicated, comprehensive theory, but in the end, we hope that a principle of renormalizability would then dictate the kind of simplicity that was required for a theory that described nature. And that is more or less what happened. It wasn't easy. In its original version, due to Enrico Fermi that I mentioned earlier, the theory of weak interactions is not renormalizable. One must, it simply doesn't work that way. If you do calculations beyond the lowest order of perturbation theory, for instance, if you try to calculate something like neutrino-neutrino scattering, you simply get an infinite answer in Fermi's theory. But we developed a theory, turned out to be a unified theory of weak and electromagnetic interactions, in which instead of Fermi's theory, in which you have a direct contact between the particles involved in beta decay, you have the force transmitted by a particle very much like the photon, but which gets a mass from the breakdown of a symmetry analogous to the gauge invariance of electrodynamics. As far as the strong interactions were concerned, the problem was different. So the strong interactions, as you might guess, are strong, which means that perturbation theory doesn't work at all. You find yourself expanding in powers of a number larger than 1, which is a dumb thing to do. But it was discovered that there are theories of the strong interactions in which the strong interactions get weak at high energy. There's a particular theory, quantum chromodynamics, and this turned out to be the correct theory of strong interactions. And putting together the electro-weak theory and quantum chromodynamics, we have now our present standard model of weak, strong, and electromagnetic interactions of electrons and heavier similar particles called leptons, of quarks, which make up the particles which make up atomic nuclei, and other particles discovered in cosmic rays. A very successful theory, a theory that's made a number of predictions that have been borne out by experiment, a theory that's, with one qualification, is not in contradiction with any experiment. And one might say, well, this is just great. This is the triumph of quantum field theory. That's it. We know the answer. Well, not so fast. There are a number of reasons to conclude that this standard model is far from being the final answer, what I like to call the final theory. At the most obvious level, it has a lot of arbitrary features. There are all those masses of the quarks and leptons that just have to be put into the theory by hand. We measure them, we put them in, there's no logical conflict, but where do they come from? Why is the mu meson 210 times heavier than the electron? Nobody knows. So that's one reason for being dissatisfied. And of course, it's out of this kind of dissatisfaction that progress always comes in physics or any other science, I suppose. Another reason for being dissatisfied is that we've left out the first known force, the first force that was ever described in mathematical physics, the force of gravity. And Einstein, we have a very good theory of gravity, which has worked beautifully. In fact, wonderfully confirmed recently with the discovery of gravitational radiation from coalescing neutron stars and black holes far away. But that's a classical theory. And in the application of quantum mechanics to it, we run up against the problem that the theory is not renormalizable. It is not a theory in which we can see how the infinities can be canceled with the cancellation of with the redefinition of a finite number of parameters. It just doesn't work. There are hints that the future theory involves physics beyond the reach of almost anything we can think of experimentally. Not quite, but almost. For one thing, as Max Planck was the first to calculate, there's a natural unit of length built into the theory of gravity called the Planck Mass. And I'm going to use these units for a while. If you adopt physical units in which Planck's constant and the speed of light are defined as 1, then the only remaining unit in which all quantities are expressed is mass, or powers of mass. And in these natural units, the constant of gravity, Newton's constant, is an inverse mass square. It's a mass to the power minus 2. And that mass is about 10 to the 18 GeV, 10 to the 18 times the mass in a proton. So that's one indication that a really fundamental understanding will involve some very large mass beyond our reach. No one, I mean, if I could convince the nations of the earth to devote the whole economic resources of the human race to doing high energy physics, which even I wouldn't try to do, we still wouldn't know how to do experiments at that energy. Another hint comes from a calculation of the way that the constants that describe the strength of the strong and the electroweak interactions vary with energy. Now you can say, well, these are constants, so they can't vary at all. But in fact, the most useful definition of these depends on the energy at which they're measured. And these constants are very different at the energies at which they're measured in our laboratories now. That's why strong interactions are strong compared to the other interactions. But if you calculate the way the energies change, if you calculate the way the constants change as the energies increase, you find wonderfully that they all come together at a very high energy. And that energy is, it's about 10 to the 15 GeV. Not that much less than the Planck scale. So there's something going on there that we can't reach experimentally, but involves some entirely new physics. Now, you may say, the question then is that physics that describes nature at a very high energy scale a quantum field theory? This is my question about the future of quantum field theory. Will it go on describing nature at a really fundamental scale, this scale of 10 to the 15 to 10 to the 18 GeV? And obviously the answer is I don't know, but we can do some educated guessing. One point I should put it to rest. You might think that since quantum field theory has done such a wonderful job of the standard model, it must be part of the final answer. Why in the world should nature at the energies we can study be described by a quantum field theory if that isn't what's going on at a really fundamental scale? Well, there is an answer. One can show, although this has never been made into a rigorous theorem, it's what one of my professors at Princeton used to call a folk theorem. One can show that within certain general limits, any theory that satisfies the principles of quantum mechanics and relativity, and one other principle, which essentially says that if you set up experiments in distant laboratories, the probabilities are uncorrelated unless you make special efforts to produce quantum mechanical entanglement. Generically, if you do an experiment at CERN and another one at Fermilab, the product of the outcomes is just the product of the individual outcomes. It doesn't depend on the fact that both experiments are going on at the same time. The technical term is the cluster decomposition principle. And given these principles, essentially any theory will look like a quantum field theory. It won't necessarily look like a renormalizable quantum field theory. But it will be a quantum field theory in which infinities will be canceled, not in general by the redefinition of a finite number of parameters, but by the definition of what these theories generically contain, an infinite number of free parameters. In these theories, which are natural low energy limits of any theory, any high energy theory, you can do a perturbation theory, not in powers of electric charge or other small parameters, but in powers of energy divided by the fundamental mass from which your low energy theory is descended. This was first done with the theory of low energy pi mesons, where the fundamental mass was not the Planck scale, but was about 1.2 GeV. And it was shown in the late 1970s that you can do calculations to generate the answer to any question about probabilities as a power series in energy divided by that fundamental mass. And that in any order in that perturbation series, and these were real honest-to-God quantum field theory calculations with loops, the same kind of clouds of created and annihilated particles that people have worried about since the early 30s. These were complicated calculations, honest-to-God quantum field theory calculations, but still, in any finite order in energy divided by fundamental mass, the infinities would cancel against a renormalization of a finite number by a redefinition of a finite number of free parameters in the theory. Although as you go to higher and higher order, as you must do as the energy increases, you need more and more free constants. So in other words, the bottom line, the moral that I'm reaching is that the success of quantum field theory in our present day does not necessarily guarantee that the fundamental theory is a quantum field theory. It could be anything. Anything will look like a quantum field theory at low energy. It seems to me that there are two outstanding alternatives, and perhaps others that no one has thought of yet. In fact, I would say most likely others that no one has thought of yet. One alternative is what I like to call asymptotic safety. It is quantum field theory in which, as we see in the standard model, the various constants of the theory vary with energy, the energy at which you observe them, but they don't vary in some random way. They approach a finite limit. they don't go off to infinity, but they remain finite and they approach constant limits. We see examples like this in many body physics. In fact, I think the Wilson-Fisher fixed point in the theory of critical phenomena, although they were interested in the low energy limit, if you turn it around and look at it in terms of a high energy limit, you see that that's what's happening there. The theory, since solids are complicated things, they are described by a quantum field theory that in principle has an infinite number of free parameters. But when you go to short scales or equivalently high energy, you find that these constants converge toward a fixed point, the Wilson-Fisher fixed point. The idea of asymptotic safety is that something like that happens, including the theory of gravitation, that there isn't any theory of gravity and weak and electromagnetic and strong interactions that's normalizable in the old way where you just have to redefine a finite number of constants. But there is a theory in which all of the infinite number of constants of the theory converge to a fixed point, to fixed points, not the same fixed point, but to various fixed points. And in order for this kind of theory to have any predictive value, it must be that the condition that since there are an infinite number of constants filling an infinite number dimensional space, in coupling constant space, the condition that the constants converge, which is the condition of asymptotic safety, limits them not to specific values, but to a finite dimensional surface, so that there still are free parameters, but only a finite number of free parameters in the theory. So far, calculations that have been done, including gravity, but making radical approximations, which mean that we can't really be sure they're relevant to the real world. But as far as it's been possible to push these calculations, it does seem that this works. That is, that the surface in coupling constant space in which the constants approach finite values as you go to high energy is finite dimensional. And so maybe these theories are possible physical theories that have some predictive value. We don't know. The other alternative, which is much more popular, much more powerful in the sense of making predictions for of a generic type, unfortunately, and has, I think, more beautiful, is string theory, which is a beautiful example of a theory which is not a quantum field theory at all, at least not in the sense that we usually use the term, but is a theory in which infinities simply don't occur at all, because strings are extended objects, not point objects. And it's furthermore a theory in which the convergence of the constants that you see in the standard model as you go to high energy still applies. If I had to put a bet, I would put my bet on string theory. But one has to admit that the theory has been around now for a while, and it has not yet developed into a theory that makes specific predictions for what we can observe at accessible energies, which is a great disappointment. I think it's much too early to abandon string theory. There are other examples for theories that worked out in the end, but took a long time to develop. I think perhaps the extreme case is the theory of Democritus that all matter consists of atoms. That took a long time to be verified, about more than 2,000 years. I hope it won't take that long. But as to whether or not quantum field theory will survive in the future, my best guess is a qualified one that it will always survive as an effective theory of phenomena at the energies that we're now familiar with. Quantum field theory will not go away. It will continue to describe weak, strong, and electromagnetic interactions, and even gravitational interactions in the approximation that the energy is much less than the Planck scale. But as to whether or not quantum field theory will survive at a truly fundamental level, well, I can say with certainty that I don't know. But if I had to guess, my guess is that it will not. Thank you very much.
Thank you, Professor Weinberg. Thank you very much for this splendid lecture. And before we proceed, as usual, I'll ask everybody to turn on their microphones, to clap our hands as a retribution for your... Okay, so let's, as I was saying, as a retribution for this wonderful talk, we have some questions, and I will allow people to make their questions. As far as Professor Weinberg is in agreement with that. But please, all of you, turn off your microphones. Otherwise, we cannot proceed. Turn also off your cameras. So please do it as fast as you can for us to recover Professor Weinberg's image. So Professor Weinberg, before we proceed, let me just tell you that during your lecture, we have had almost all the time 250 participants. That is the upper limit of this platform that we are using. I'm sure that if we had 50 or 100 more, we would have all these people in addition to this 250 that we had. So thank you very much, for this opportunity of Brazil to listen to you, to this wonderful talk. Just as a registration of what, so we had almost all the federation units of Brazil represented in participants in the audience. And more than that, we had people from 3 different continents, apart from Brazil, obviously representing America, as well as you are. We had people from Europe, like Spain, Netherlands, and Portugal. And we had also people from India, therefore from Asia, people from Chile, and many others. So let us then start with the question. Is it okay that we proceed with the questions, Professor Weinberg?
Yes, I'm not going anywhere.
Okay, thank you very much. So the first registration of a question that I have here is from Mauricio Calvão. So Mauricio Calvão, you can turn on your microphone and do your question, please.
Thank you very much, Professor Weinberg, for your excellent lecture. And I would like you to dwell a little bit more, if possible, on the question of does gravity necessarily have to be quantized, or might it just be a kind of effective theory and there would be no sense to quantize it? Thank you.
I can't Well, everything has to be quantized because quantum mechanics is true. And I can't imagine that the principles of quantum mechanics apply in some places and not other places. Now, it is conceivable that gravity is some kind of collective phenomenon, and we would be making a mistake in applying quantum mechanics to the gravitational field as introduced by Einstein. I mean, after all, we can make a contour map of Brazil, say, which shows rivers and mountains and so on, and write a function which gives the altitude as a function of position, call that a field, but we wouldn't quantize it. It's just a description of the topography of Brazil. Maybe the gravitational field is something like that, but I suspect not. Recently, I did a calculation with Raphael Flauger in California about the absorption of gravitational waves from distant coalescing sources, black holes and so on. And at first, our calculations showed that very long wavelength gravitational waves would be absorbed by a process called reverse Bremsstrahlung, in inverse Bremsstrahlung, in the gas in intervening galaxies on the line of sight between us and the source of gravitational radiation. And then a colleague here in Austin reminded me of the process of stimulated emission, which was first introduced by Einstein when he applied quantum mechanics to the radiation field, which showed that, and this is a strictly quantum mechanical process, that atoms in the presence of a radiation field are stimulated to emit more radiation. This is the principle of the laser. And unfortunately, the effect of that in this case is that it wipes out the absorption. For every absorption of a gravitational wave, you get a stimulated emission, which restores the gravitational wave. So the effect that Flauger and I were calculating just isn't there observationally. Well, that's an application of quantum mechanics to the gravitational field. Of course, you might say, if I wasn't interested in applying quantum mechanics to gravity, I wouldn't have thought of inverse Bremsstrahlung in the first place. It's conceivable that but I don't see any reason why quantum mechanics should not be applied to the gravitational field. In fact, I would say it more strongly. I'm sorry, I'm going on very long here, but this is something that I've worked on, I feel strongly about. You can ask, why does gravity work the way it does? Well, on a classical level, you can explain it, and I did explain it in the textbook that Professor Crispino was kind enough to mention, Gravitation and Cosmology. I emphasized the role of the principle of equivalence. That is, that there's an equivalence that Einstein was the first to point out between gravitational and inertial forces. You can say, why is that true? It's a consequence of the fact that gravitational and inertial mass are equal. Well, why is that true? There is an answer, and it comes from applying quantum mechanics to the theory of massless particles of spin 2. If you imagine a particle which is just like a photon, zero mass, but instead of spin 1, which is the spin of the photon, it has spin 2, you'll find out that that particle must interact with energy and matter in such a way that the strength of the interaction, which we call the gravitational mass, equals the mass that appears in the energy and momentum, the inertial mass. In other words, any theory of mass zero and spin 2 must behave the way gravity behaves according to Einstein. So to me, the explanation of Einstein's theory, certainly not the explanation he would have offered, is that it is the theory, it's the quantum theory of particles of mass zero and spin 2, in the same way that electrodynamics is the quantum theory of particles of mass zero and spin 1. And I suspect that's more of an answer than you expected. I'll take another question.
Okay, thank you.
Thank you. Thank you, Maurice. Thank you, Professor Weinberg. I have a question also from Giorgio Torrieri. Giorgio, do you want to make it yourself?
Sure. Thank you very much for a great talk. About your main topic, there is also infrared. I mean, we know that we live in a world with broken symmetry, which is only possible when the Stone-von Neumann theorem doesn't apply because the degrees of freedom are infinite. Wouldn't you say, and there is effects also like the Unruh effect and the Hawking radiation, which also rely on things like unitary inequivalence, wouldn't you say that these are infrared phenomena? Wouldn't you say that this is evidence that quantum field theory, the infinity of degrees of freedom of quantum field theory, is somehow fundamental as well?
Yes, I suppose so. I can't imagine. Obviously, when you talk about a field, you are talking about an infinite number of degrees of freedom. I think that's a nice way to look at it. I hadn't quite looked at it that way, but that's an interesting perspective. Yeah, quantum field theory is certainly a theory with an infinite number of degrees of freedom, and we have to live with that. Fortunately, we can live with that and do calculations, and they work.
Okay. Thank you, Giorgio. Thank you, Professor Weinberg. So I have here a question from Satish Kumar VH. I'll read it. In your opinion, what are the open problems in quantum field theory that young people should be working on these days?
Well, if I knew what they were, I wouldn't tell you. I would work on them myself. I'm better at suggesting things for experimentalists to do. And in fact, this is something I wanted to mention in my talk. I'm glad to have a chance to bring it in now. There are signs, experimental signs, of a higher energy scale beyond anything that I've talked about. The standard model, as I look at it, and I think most people look at it today, is a low energy limit of a theory that comes down to us from some very high energy scale, like 10 to the 15 or 10 to the 18 GeV. Now, that theory, there's no particular reason for it to be a renormalizable theory. Just like the theory of low energy pi mesons I mentioned earlier, it's doubtless a theory in which there's an infinite power series in powers of energy divided by that very large mass, in which as you go to higher and higher order, you get more and more constants. Now, you can imagine going to one order higher than the one we've gone to so far, considering terms that might be added to the original standard model with one power of energy over mass taken into account. When you do that, in the very simplest addition you can make to the standard model, you're adding a new interaction which is not in itself renormalizable, involving a pair of lepton doublets, that is neutrino and electron, together with a pair of scalar or Higgs doublets, And the effect of this is to produce an electron mass, which is suppressed by one power of a very large mass in the denominator. The estimate you can make of the mass produced by this term is of the order of 300 GeV square, which is the 300 GeV is the expectation value of the Higgs field, divided by, let's say 10 to the 15 GeV. And this is what you would predict for the mass of the neutrino arising from this kind of interaction. And lo and behold, it works. Neutrinos do have a mass that's of that order of magnitude, a little bit less than an electron volt, first discovered in neutrino oscillations and neutrinos from the sun, and now thoroughly verified in terrestrial experiments. So I really had meant to put this into my talk, but I wasn't reading my notes, so I forgot to mention it, that we do have one piece of data coming from very high energy, the neutrino mass. And my advice to young experimentalists would be to look for others. In particular, when you go to the next order in 1 over m, where m is this huge mass, you find processes like proton decay. And that would be my advice, is to sit underground in a quiet place with a large amount of liquid and look for flashes of light indicating the decay of a proton. Now, as far as calculations for young theorists, that was the original question. I don't know. I think I would work on string theory, although I think we need new ideas there. If it's just a question of taking the theory as far as it's been developed, I'm not sure it's worth that effort. I don't have good advice for a young theorist. I wish I did. And as I said, if I did, I wouldn't tell you.
Thank you, Satish. Thank you, Professor Weinberg, for this very nice answer. So now Antonio Duarte Pereira Jr. has a question. Antonio, do you want to make it yourself?
Yes, thank you, Luis. So thank you, Professor Weinberg, for the very nice lecture. I would like to ask you about the asymptotic safety scenario for quantum gravity. So I think one of the biggest challenges there is the fact that if the fixed point exists, I mean, we cannot probe it using perturbation theory.
Yeah, absolutely.
And therefore, I mean, we don't have systematic tools in order to convince people that the fixed point exists. So in your opinion, I mean, do you have any visions on how to probe this fixed point, or what would be the best strategy in order to really find the evidence for the existence of the fixed point?
I completely agree with you in your statement of the current problem. Wilson and Fisher they also dealt with a fixed point that what they called non-Gaussian. That is, it was large enough so that you couldn't do a perturbation series expansion and powers of the fixed point. What they did instead was to consider the limit as the number of dimensions of space, which is 3. They were working in a classical field theory in 3 dimensions, approaches 4 space dimensions, where the fixed point would be just the coupling constant of an ordinary or normalizable theory. And by working in a power series in D-4, where D is actually 3, they were actually able to get results that worked. It's always been amazing to me that the numerical calculations that they did worked as well as they did. Maybe something like that can work in the theory of asymptotic safety. That was my earliest thought about this, and so far, what's been done largely in Germany, for some reason, is to take a theory and truncate it. That is, only consider, for instance, in quantum gravity, only consider a certain number of powers of the curvature scalar, and only consider the renormalization of that finite number of constants. And what I mentioned as a hopeful sign is that then you can actually do calculations, although you don't necessarily believe the answer. But what they find is that the surface of constants, which is attracted to the fixed point, has a lower dimensionality than the total number of constants they've introduced by the truncation of the series in powers of the curvature scalar, which I regard as hopeful, but it certainly doesn't take you all the way to convincing you that this is going to work. I don't know. I don't know how to, obviously, again, if I knew how to do it, I would do it. I don't know how to do calculations there that really would give you a believable result. But we have to find something in the end that maybe mankind isn't smart enough to ever do any calculations except in perturbation theory, but we can be clever and think of different things to expand in powers of, as Wilson and Fisher expanded in powers of dimensionality -4. Maybe we can think of some clever thing to expand in, but I haven't thought of it.
Okay. Thank you, Antonio. Thank you, Professor Weinberg. There are many comments here with compliments to your talk, like, thank you very much, Professor Weinberg. I appreciated your clear and didactic explanation. So many compliments. Felipe Augusto has written a question similar to the previous one. As someone who had its adventures on particle physics and gravitation-related areas, what advice could you give for young graduate students which are deeply interested in both areas? So if you want to skip this one, either answer. I have another one. So Manuel Malheiro is asking, can time be quantized? So please choose.
Well, as far as the first one is concerned, I wouldn't be too critical about the work you do. Speaking for myself, I have written a large number of thoroughly unimportant papers. I just looked up the first paper I ever wrote, and in, I don't know, about 60 years, it has gotten a total of 30 citations. And that's not an injustice. The paper was not important at all, but it got me started doing research, and that's advice I would give: to get research problems to work on. They are tremendously educational, even if what you do in the end interests no one except your immediate family. Work. Don't sit around being too critical. Read the literature, find things that you don't quite understand, and try to improve on what's in the literature, even if it isn't terribly important. Keep busy. That's my advice. It's not very profound advice, but the other question about quantizing time, that actually reminds me of a class I took when I was a graduate student in Princeton. It was a class on quantum field theory given by Arthur Whiteman, and at a certain point, a student raised his hand, and said, why are we bothering with this? What we really have to do is to quantize length. And Whiteman got very angry and pointed at the student and said, you quantize length. So I'm tempted to point at you, except I can't see you with this system, and say, you quantize time, and let me know how well you do. There is a serious question whether space and time are emergent phenomena. I attended a session of the Solvay conference devoted to just that issue, chaired by David Gross. Will the ultimate theory involve space and time at all? I think that's a better way of putting it than just to ask whether you will quantize space and time, whether space and time emerge in a low energy description. It may be, but that, if that's the case, then we're really far from an answer. I hope that human beings are biologically capable of answering these questions, but so far we haven't. Another question?
Okay, thank you, Felipe Manuel. So I have here another question of Armando Brizola. Thank you, Professor Weinberg, for a nice lecture. I'd like to ask you a simple question. In face of infinite renormalization, do you think that quantum field theories are mathematically consistent?
I don't really care. There's a standard of mathematical rigor that some physicists have pursued. It doesn't bother me. We have to do approximate calculations in any case, and we know how to do them, and the rules are mathematically consistent. The results make sense. They agree with the experiment. I'm a modest person. I don't ask for more than that. A mathematical rigor is, it may be too much to ask for. Maybe when we have the final theory, we can spend some time thinking about its mathematical consistency, but that has not been the path of progress. There's been a lot of concern about the mathematical rigor of quantum field theory, its mathematical consistency. I'm not an expert in the area, but as far as I know, none of that has led to the kind of progress that we have seen in my own working life, since the 1950s, I would say, in physics. So that's my frank answer. I don't know the answer, and I don't much care.
Okay. Thank you, Armando. Thank you, Professor Weinberg. So Olivier Piatella wants to make a question.
Yes, please. Can you hear me?
Yes, I can hear.
Thank you very much, Professor. And let me say before the question that it's a great honor to make a question to you after I studied and read all your books, and I make them study to my students too. So you are a source of inspiration for my work since when I started to do physics 20 years ago. So thank you very much. And my question is, I would like to know your point of view. What do you think about dark matter? And if there's physics beyond the standard model there? Thank you very much.
Well, yes. I mean, certainly there's physics beyond the standard model, because there's no particle in the standard model that could account for dark matter. There are moderate extensions of the standard model that could provide dark matter. There could be sterile neutrinos or axions, which involve introducing a symmetry that might be necessary in any case. And obviously, the outstanding example is supersymmetry. Supersymmetry is an extension of the standard model. So far, there's no sign of its correctness, but it's mathematically beautiful. And in a way, it's the most obvious direction beyond the standard model, and it provides lots of candidates for the dark matter particle. I'm impressed by the fact that if you have particles with masses in the range that we observe, 10 GeV, 100 GeV, that interact in the kind of interactions that we observe, whose strength is like the weak interactions, but that are stable but annihilate only in pairs, so that as the universe expands, they're less and less likely to find each other to annihilate. That in that kind of theory, the dark matter density that we observe is roughly what you would expect. Of course, I'm being very careless with factors of 10. It's not a precise prediction, but you could turn it around and say, if you take what we think is the observed density of dark matter as observed in gravitational phenomena and ask what mass of this kind of particle would be required, it is of the order of 10 or 100 GeV, not unreasonable. But it still is a particle that goes beyond the standard model. But it may be a very modest modification of the standard model. That is certainly, you know, someone asked me earlier, what should a young theorist work on? Dark matter is a great example of something to work on. I sometimes, looking at the published literature, I think half of the young theorists in the world are working on it. I don't have any new ideas about what dark matter could be, but there is dark matter, and there are lots of directions from the standard model that would produce candidates for dark matter. So that's certainly something I would work on.
Okay, so thank you
very
Oliver.
much.
Thank you, Professor Weinberg. So I have a question.
It's running out of fluid, so I think I'll just take one more question, if I may, and
Okay.
call it a day.
Okay, so Valentin has a question. He wrote, how can quantum field theory help us to understand rate of matter creation on cosmological context?
Well, again, one has to go beyond the standard model. Sakharov described several criteria, that all of which have to be satisfied for a theory to produce an excess of matter over antimatter, which we know exists in the world. You don't need much. If you go back to the time at the end of the first 3 minutes, no, I think you have to go back earlier than that. But if you go back sufficiently early, there was one extra matter particle for every 10 to the 9th matter-antimatter pair. So the matter excess is in a sense small, and Sakharov pointed out some criteria for producing it. One is you have to go out of thermal equilibrium. Well, you can do that if you have a very heavy particle with a delayed decay that decays after the temperature is dropped to the point where the decay products will reconstitute the particle. You need a violation of symmetries like CP, the product of charge conjugation, invariance, and parity conservation. And we know in the standard model various mechanisms for CP violation. In fact, there's a good deal of study of whether the neutrino masses violate CP. Recent experiments show that the mass matrix of the neutrinos do violate CP. Maybe that provides the CP violation that you need. So again, there are lots of extensions of the standard model that can account for the excess of matter over antimatter. And that's, again, a good clue of how to go beyond the standard model. And it doesn't have to be a profound extension, like going all the way to string theory. It could be something like just adding another kind of field or another kind of symmetry. Even this dimension, this operator that I mentioned that gives neutrinos a mass could be the source of the CP violation that I mentioned, although how that works out together with Sakharov's other criteria, I don't know. I think thank you very much. This has been very stimulating. Thank you for your very good questions, by the way. I'm sorry I wasn't there to see you all. I feel it's a great privilege to have been able to talk to you.
Okay, Professor Weinberg. I mean, it has been a wonderful opportunity for us all. So as we come to the end, I will ask everybody to turn on their microphones and clap our hands in acknowledgement to your very...